You're in now. Okay then, so we're almost there. Differential equations. So this is our last part really. Differential equations, understanding what they are and doing some work with them. And then the next part will be trying to solve some in context. So differential equations are not like regular equations. Like that might be a regular sort of equation that you might think about so far. Differential equation has a y and an x, but it also has a derivative in it as well. So you can have equations that look maybe something like this. Okay, you've seen something a little bit like them maybe when we were doing implicit differentiation. So we can solve these equations. And when we say solve, what we mean is we turn it into y is some function of x. Okay, normally y is some function of x, or y equals blah, 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 something about x. Okay, that's what it means to solve. In other words, we don't see the derivative part anymore. So let's have a look at an example. Find the general solution. General solution. This implies that there's going to be a plus c. Okay. You'll see different questions that we'll talk about other solutions in a moment. General solution plus c, which also implies integration. And that's what we're going to have to do at some point to try and remove this dy dx. However, we want to do something else first. So these are the main steps normally. So what we want to do is we want to, first of all, separate variables is what this is called. So I want to do some manipulation with this equation so that one side is all about y stuff and has a dy there. And then the other side has x stuff and then a dx there. So all the y's are on one side, all the x's are on the other. How could I do this? Well, if I keep the dy on the left and I bring the dx up, the problem is the x's and the y's kind of stuck together. So the first thing I could do is I could do some factorization. These both have a y in them. So I could factorize that and say that's the same as x plus 1. And what this would allow me to do is now to sort of like divide pieces in such a way where I get all the stuff about y on its own with the dy and all the stuff about x with the dx. So it looks like this. So we do this one here. We bring the y to the other side. So 1 over y equals dy dx equals x plus 1. And in fact, I'm going to just do this on this part here as well. You can also, you can treat this dy dx like a fraction. And if you multiply by dx on both sides, you will get this here. And now what does that look a little bit like? It looks like you're doing an integration. Okay, stuff about y with dy, stuff about x with dx. And that's what we'll do. We'll actually integrate both sides. And because you've got all of the y's together on the left and all of the x's together on the right, you can integrate your y's on the left, it fits the notation, and you can integrate your x's on the right. Let's have a look at that. So we've got this one here. Yeah, I mean, we've kind of covered this one already. Okay, it looks like this. We integrate on both sides. 1 over y, if you're integrating with respect to y, it's the natural log of y with those absolute signs there. And then over here, this is a regular one. The c, now you might ask yourself, why does the c appear on the right-hand side? It's completely arbitrary. You actually have a c on the left and on the right, but if you collect it together, it's a c. And we normally put the c here on the right-hand side. Now, what was the question? The question was find the general solution. So that's why there's a plus c. And dy dx is gone, but natural log of y, we don't need to leave it written like that, okay? So what we could do to undo the natural log, if you like, is we could do e on both sides, okay? That will give you y, but over here it will give you a really, really complicated power, because if you're doing e to everything, you'll get e to the half x squared plus x plus c. Now, using power rules backwards, this is the same as e multiplied by e to the power c multiplied by e half x squared plus x. And just check, if you use the rules, it takes you back to this one here. Now, why do we do this? Well, the c is just some number, okay? And often we don't have to work that out there and then. So e, which is a number to just some number, is also just some number. And to make things a bit neater, we tend to write this as a. So the right-hand side ends up looking like that. The left-hand side, e and the natural log are inverses, so they cancel each other out. You get y equals, and you get this one here. Okay, so the general solution, in other words, the way to remove the dy dx to make it so it's no longer a differential equation is like this. So this is solving a differential equation. Let's do another one. So find the general solution to this one here. So step one, we're going to talk about separating variables. So the same thing from before. One side needs to be about y's, one side needs to be about x's. And you want to multiply and divide in a way to achieve this. So tan y, that's about y. X is about x. The dy is already up here. So if I can, I'd make the left-hand side dy. And if I move this one up, yeah, okay. I can see 1 plus x squared dy equals x tan y dx. But then you want to move that part under as well to put the x's with all the x's. And you want to put this part on the other side. So if you do all of that, you will end up with this one here. You could write cot y if you want to, but you don't have to do that. And then when we are in this position here, we will be able to integrate. Okay, so we separate them and then we integrate. So cot y, I think this is one that's in your formula booklet. Okay, natural log of sine y. And over here, well, you've got a reverse chain rule or substitution, however you prefer to solve it for this one here. Okay, plus c. And again, we said plus c, we tend to put on the right-hand side. Same as before, what does it say? It just says give the general solution. So we can try and get y on its own. We'll put e on both sides then. Remember, e to the c will be a. That's one way you could do it. So you could say sine of y, because those parts will cancel, will be equal to, if I put e to the c, that could be a, and then e to the half, natural log 1 plus x squared. There's lots of manipulation you can do here. You could move that half up there if you wanted to. There's loads of things we could do. Let's have a look at what they do. So I'm just going to comment on this in a moment. This is just another approach that you can do. So what have we done? Well, we did sine y equals all of this stuff up here. We could move that up there. So we could get sine y equals yeah, I mean, we are going to be able to do something equivalent. So I'm just having a look. What they've done, and the reason why they've done it, is they've spotted that this is about natural log, and this is about natural log as well. Sorry, up here, this is about natural log, and this is about natural log as well. Now, you could go down the road of doing something like this and whatever, but it could get quite complicated. What they're saying is maybe before we use e to try and get rid of the whole thing, maybe we can try and change everything into logs. Now, the problem with that is you have this c here. Remember, c is just a number. So the trick is to say, well, just some number is the same as the natural log of just some other number. Like, let me give you an example. 100, or no, let's do 2. 2, let's pretend c was 2. Well, 2 is the same as the answer to log 10 of 100, isn't it? Yeah. They're the same thing. Log 10 of 100 is 2, c is 2. Well, why would you do that? Why would you make things more complicated? Well, you might do it so that the other part has log in as well. Because if you have log in all of these parts here, you can use log rules to simplify things a little bit. So they've used log rules. So they put the half as the power here. That's where the square root comes from. And then when we have natural log of something plus natural log of something, it's the same as the log of the product of those two. So you end up, bear with me here, you end up multiplying those together and you get that part there. So it just makes it a little bit more concise, a little bit nicer to deal with. It also means when you're at this stage here, if you have natural log on both sides, well, if you do E cancels them out quite nicely. And sine y to y, you just do inverse sine, which is called arc sine. Okay, so yeah, we'll scrap that one on this approach. Because there was lots of natural log in the question, for this one, it makes sense to try and express everything in the same base log so that you can tidy things up nicely. Quite a hard example, that one there. Okay, that's quite a tricky one. Let's do one more. So we're going to have the same question again. It's now got a boundary condition. So a boundary condition is like a coordinate. So we're going to have one of these questions. We're going to answer the question. We're going to have some plus C or A or something like that, some number we don't know. But then we're going to use something that we do know about the situation to help us fully answer the question. So there won't be any unknowns in this. This one here then, so what would we do? We could divide that one to the other side, keep this as it is already. You could keep the -3 there. They've kept the -3 here. The thing you have to be careful with this is the numbers. You can always move the numbers to the other side, but you don't have to. So you will see slightly different answers depending on what solutions you look at. You do need to make sure the y -2 is over here, though. That's one thing you have to do. So you split it up like this. The left-hand side is nice to integrate. The right-hand side is a problem. It has a product in the denominator. If there's a product in the denominator, you would use partial fractions. So quite a few steps here. Let's pretend you've done all of that. So this part here is the same as this part here, okay? We've separated them. Y is on the left with dy, x is on the right with dx, and then we integrate. So that's a nice integration there. That's a nice integration. This one you need to be slightly careful. There's a reverse chain rule because of the 2x. So it should look just like this. And then you would have a plus c, wouldn't you? But what did we just say in the previous one? We said if there's natural log everywhere, it sort of makes sense to change c and think of c instead as the natural log of some other number, because then it will let you sort of push all of that together. And in fact, that's what's happened. Can you see the whole right-hand side there has become this by x plus 2, 2x plus 1 in the denominator, and then the plus k means you multiply these together. Okay. Then when you've got logs on both sides, you use e, and you get this one here. And you could add the 2 to the other side. And at this stage, they've decided, well, let's use this information here. So k is the only thing we don't know if we put our x and our y in for a given value. So this will allow you to find k, and it allows you to come up with a complete equation. Okay, so it's not a general solution anymore. You can do this. You can put these numbers in any time after you integrate. And I think you're going to see with some examples a little bit later that often it's good to try and do this sooner rather than later. Yeah, it tends to make things easier when you do it sooner rather than later. So pause the video and have a go at this one here. What I'd like you to do is step 1, you're going to separate the variables. Step 2, you're going to integrate. Now, this one here, you're going to have to use this. I want you to look at your solution after you integrate and to make the decision. Should you use it straight away, or should you do some manipulation first before you use these values here? But essentially what you will be doing is you will be substituting in the knowns to find, it will be C or it will be K or whatever happens to be in this situation. Okay. And if possible, it's not always possible, we often look for an answer in the form y equals some function of x. Pause the video and have a go. And let's take a look. So separating variables, the y needs to come up. That y there needs to go up to the other side. This x needs to go up there. And that is enough. So integral of y dy equals 3 sec squared. They've written it as sec squared because integrating sec squared, that's quite a nice question because tan differentiates to sec squared. So we've got this one here plus c on our right-hand side. They've chosen to put the values in straight away this time. And if you put those in, it gives you c equals -1. You'll often find that c equals nice numbers like 1, -1, 0. Sometimes it's more complicated than that. Sometimes you can have c equals natural log of 4 or something. But once you find that, then you put it back in. And in this case, they've left it as that. It doesn't always have to be y equals some function of x. It will say if they want you to do that. If it's y squared, it's often nicer to just leave the answer as y squared. So I think here I would probably leave this as y squared equals 6 tan x minus 2. That's how I would leave my answer. Lots of ideas there then. So you need to get y typically on the left-hand side by dividing. If it's a harder question, you might even have to factorize to separate the y's and the x, and you're only moving them around by multiplication and division. Okay, no addition, subtraction. It's multiplication, division to move these around. If there's lots of log, especially like on the right-hand side, it's good to have c written as log k, and that allows you to combine logs together. So you might see situations like this. So there's a few things we could do here. First thing is we said if we want to use log rules, there must be no number in front of log. So you would make this first of all log of x plus 1 squared. You can lose these signs because x plus 1 squared is always positive. So you do something like this, and then you combine them together. So this is the kind of step that you will see happen quite a lot. Okay. Yeah, we'll do that because of the x. The boundary conditions. So like you've seen these in mechanics before when you've integrated and you've been told to speed and stuff. It tends to be easier to do them sooner rather than later. And you should expect partial fractions, logs, all of this stuff to come together now. So that lets you get on with 11J. And in the next video, we'll do some harder contexts together.